So let's suppose that you have a plane, and that plane takes passengers from LA to Washington, D.C., and then that same plane goes from taking passengers from Washington, D.C. to Boston. And if you have a passenger who's on, both those flights, and the passenger says, well, I want to know how far I've traveled if I had just gone directly LA to Boston. This is an example of a vector addition problem. So if we think about the vector u being some vector from LA to Washington, D.C., and v being a vector from Washington, D.C. to Boston, then we can think about the idea of if I went from LA to DC and then went from DC to Boston, this would be my final destination. So when we think about any type of vector here, we want to think about the properties. So if I have two vectors, u and v, and I have any scalar c, then if I add those two vectors together, so over here, if I add those two vectors together, straight lines are helpful, but you're not going to get one today. Well, sorry. All right, so if we think about adding two vectors together, all we really need to do is add their components together. So if I wanted to decompose, if I had this vector here, what I'm really doing is I'm taking the x distance in u plus the x distance in y, and I'm taking the y distance in x distance in u and the x distance in v, and then I'm taking the y distance in u and the y distance in v, and I get there. So I take, if I go out to here, that's the x distance in u. If I add the x distance in v, which is that, I start here, I take the y distance in u, and then I take the y distance in v. I get there. It's not perfect because I'm doing it with my hands, but the idea is there that you're just, when you add the vectors, you get a resulting vector that takes you directly to the point of adding those components separately. Now, scaled vectors are kind of important. So we use this all the time. This is all the time in any kind of vector analysis. So imagine, if it was something to the effect of, if I did this much work pushing an object in this direction, if I did 100 newtons of work by just pushing an object 10 meters, right? Well, if I double the amount of distance that I go, then I double the work. So when we think about a scalar, the word is scalar. Scale is the root word here. So we're scaling a vector. So if we're scaling it, well, then we're really just taking a number and multiplying it by each component. So see, any number times a vector, any scalar number times a vector, scales each component. So if I were to take the vector u, and add it to itself, right? So this vector will be 2u, right? Because it's twice the vector u. So not only can I scale that way, I can actually shrink a vector. And we're going to use that when we talk about unit vectors. So think about negative v. If you think about negative v, well, that would be the vector in the opposite direction. So if the red vector v here, is going from Washington, D.C. to Boston, well, then negative v is going from Boston to Washington, D.C. So negative v is the same vector in the opposite direction, which that's negative v1, negative v2. Which you probably could have guessed that just from property 2, right? Because this is just a negative 1 in front. So, negative v2. Good catch. All right, so finally, if I have u minus v, well, if I know what u is and I know what negative v is, I'm really just adding negative v here, which may be overthinking it. Again, realistically, if I'd given you if I had asked you, if I didn't put this on here and had given you like multiple choice questions on which ones were the, what the right properties were, you probably could have just guessed them. Because it's very intuitive. It's just simple, right? Multiply a vector, you're just multiplying the components. Add a vector, you're just adding the components. Subtracting components, again, negative v is really just a special case of 2. So that's the component properties.